Today is 14th of November. And we are continuing discussion on the phenomena of neutrino mixing and oscillations. We have derived an exact expression for the probability between flavor oscillations. We have introduced theta, the neutrino mixing angle, and the mass square difference this is the main characteristics of the phenomena of mixing and oscillations, and we have derived the probability of oscillations between two flavor states. We consider the case of two flavors and two mass states. Yeah? And as a result, I ask you to try to examine the problem that sounds as follows. What is the maximal degree of suppression in the particular neutrino flavor after the flux of neutrino with the initial flavor travels a distance x from the starting point to the detector. Suppression of the particular flavor after the flux of neutrinos, the neutrino flux, travels the distance x from the source to the detector. This is what's the problem. And I ask you to solve this problem. Well, I am sure that everybody has done this, and nevertheless, I will probably repeat what you have already done. Okay? So, the solution. The solution. Let's consider n neutrino flavor species. Species, понимаете, что это такое, да? Ну, типы, да? And n mass states. So we have n flavor neutrinos. This is the state of neutrino. Flavor can be whether lacton, muon, tau, and probably some other flavors. But we know, we have discussed with you that according to the present knowledge and experimental data, we have only 3 flavor neutrinos. We have discussed this or not? Not yet, but I will make a comment a little bit in just a moment. And also we have mass states or physical states of neutrinos, and we just enumerate them by I, that can be equal to 1, 2, 3, etc., probably n. Obviously, the number of flavors and flavor states and the number of mass states will be equal, because this. Well, I would like to make a comment about the number of flavor states. According to the present knowledge, according to the present experimental data. So there are inevitable consequences, that experimental consequences that can be attributed and can be recognized as an indication for what is the number of active flavor states. So even many years ago in lab, this is the accelerator that was in CERN before the Large Hadron Collider. And this is a famous machine. They have a lot of gifted results obtained, but one of the results was the measurements of the Z boson width or probability of decay, in other case. Yeah? Well, and this is the check of the standard model. The check of the standard model. And according to these checks, one of the outcome was the probability of the width ширина of this boson decay. And according to the standard model, from the Lagrangian of the standard model, yeah, it follows that there is coupling between this boson and neutrinos, neutrino and anti-neutrino. Obviously, there are flavor states. So the diagram is like this. This is a Z boson, and this is the lines for neutrino, anti-neutrino. Yeah, flavor. Yeah, and flavor equals to 1 or electron, muon, tau, etc. And the width of depends on the number of these diagrams. And from experimental observation, it follows that the number of neutrino flavors is equal to 3 plus minus some small delta. So it means that now it is well confirmed that there are only 3 flavor active neutrino states. You have heard, and also I have already mentioned, that people are considering the 4th, the 5th, and some extra neutrino species. But they should be sterile neutrinos, because there is no room to participate in these kind of processes. It means that they can exist, but they have no right to be coupled to the boson. In other case, the width will be changed. Yeah. So I will put like this. This is a continuation of our remark about sterile neutrinos. Sterile neutrinos. They can exist, sterile neutrinos, without interaction with other particles. So they cannot participate in interaction with other particles, including interaction with the Z boson. But how they exist and how we can recognize that this particle exists? They can participate in other connections with our existing particles by mixing. So there is no interaction, but there is a mixing. So in this case, we, in addition to flavor neutrinos, where F equals to electron, muon, and tau, we have in addition sterile neutrinos. And these sterile neutrinos can be whether 1, 2, 3, etc. It can be numerous sterile neutrinos. And they are included to the game. So they should have an observable consequences. And they should be connected somehow to other particles, but not through interaction in the standard model. They are not interacted with the normal particles, but they are mixed with other flavor neutrinos. So it means that if we have only one unique sterile neutrino, we should go to the 4 mixing matrix. So, and in this case, we have introduced neutrino mass states, physical states like neutrino 1, neutrino 2, neutrino 3, and neutrino 4 with masses, in general 4 different masses, and we also should add to the normal flavor neutrinos 1 sterile neutrino. And each of these guys now should recognize as a superposition of these 4 states with different masses. So the sterile neutrino participate in the game. They can have observable consequences in the flux, by the way, in the measured flux of the solar neutrinos. So if there is 1 or 2 or 3, any number of sterile neutrinos, and if they are in mixing with the flavor with the other neutrinos, so it means that it will influence the flux detected in the Earth, in the solar neutrino flux. New options, new possibilities for neutrino, electroneutrino to oscillate to other flavors just appears. And there are a lot of experiments, by the way, searching for sterile neutrinos. This is one of the open issues, key issues of the nowadays neutrino physics. The searches, the theoretical studies of the effects of the sterile neutrinos. It's not excluded, and a huge amount of experiments have a special program to detect the sites, the results of the sterile neutrinos, which can mix with normal neutrinos. And that's why I just put in the task, in the problem, n, because we do not know. Maybe there are some sterile neutrinos also, yeah? And this is like a remark about sterile neutrinos. Probably I haven't mentioned this, yeah? Well, but the stable, the basic result is that we have only 3 active flavor neutrinos. Active means that interact through the big interaction theory, electroweak interaction theories, and that is described by the Sternmon Lagrange. Okay, this is a remark, so let's go ahead. So each of the flavor neutrinos is a superposition of the mass states. It is sum of the mass states. This is the mixing matrix element, and this is the mass state. So, and now we can write the probability of the transition, the probability of the transition of neutrino of the type F1 to neutrino of the flavor type 2 during the flight that is lasted through some time t, yeah? And we have derived this probability on the last, our previous lecture, that this probability, this is a probability of oscillation. I just instead make a shorter notation, yeah? F1, I just put 1 to flavor 2 as a function of time, equals to, we have derived this formula, I equal to j to n. We have number, the number of flavor and mass states. This is the squared of the mixing matrix, F1 I U F2 J, yeah, plus double sum I not bigger than J, U, 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 U. These are elements of mixing matrix. And now we should properly indicate the indices Li, Fi, Fj, and j, okay? And then cosine, we have derived this expression, 2 pi's. So the evolution in time for relativistic neutrinos is equal to the evolution along the distance, because neutrino is traveling nearly with the speed of light. Yeah? So we just use always this prescription. And I will put x divided by the oscillation length, где L, Ij, we have derived this expression, 2 pi's, double energy of neutrinos, divided by modulus of mass square difference of 2 neutrinos. Yeah? Okay. So, if you remember, according to the needs of the real experiment, I mean, if you just taking into account or just considering the solar neutrino experiment, when neutrinos travel a rather long distance, and also it is not clear for which particular point inside the side each of the neutrino were produced, we have to make an average over the time or x, because the starting point is not fixed for each particular neutrinos, and in order to use this expression to explain and the experimental data we should average over t or x. Yeah? So the average probability also we are interested, according to the task, in the survival probability, yeah? Because we are searching for the maximal degree of suppression. So it means that first we have to find the survival probability, and then to examine when the survival probability got its minimal value. That will be realization of the demand that is maximal suppression is achieved. Yeah. So in addition to average over time over t, we have also to add the following condition that f1 equals to f2, and let it be the electron neutrino. Probably this is not. You understand, this is a neutrino flavor F1, neutrino flavor 2 equal to electron neutrino. Okay, yeah? I think you follow my notations that are flexible a little bit. Then the probability, just from this formula, is simplified to the following very short expression. This is equal 1 sum over I from 1 to n. This is the number of flavors or mass states, and here is the mixing matrix element to the fourth, yeah, because they are identical. I just missed they are identical to the fourth. Okay, this is what we get, the average survival probability. Okay. And now the question is how to find and how to answer the question when this value would get the minimal, gets its minimal. Yeah? Okay, I just make like plus. So what we have? We have to find the minimum of this probability under the condition that neutrinos do not escape and evaporate on the path from the source to the detector. Obviously, there is a condition to the elements of the mixing matrix. In total, the number of neutrinos remain the same. Yeah? There are no extra neutrinos appeared during the path or just escaping neutrinos. The number of neutrinos is the same as in the beginning in the sun as in the detector. So, and this condition has the following visualization. This is the sum of all probabilities, the sum of all probabilities of conversion equal to 1. So, neutrinos do not escape, do not appear additional number along the path. So, this is a typical problem that you know how to solve if you just have already passed the first year of mathematical analysis in the university. This is the extremum with a condition. And I would like to recall that this solution can be achieved using the Lagrangian multipliers. Yeah? So we have to construct a functional accounting to this exact expression for this condition, then find a minimum of this, and then get the solution. What is important that everything depends only on the elements of the mixing matrix, neither on the mass square difference nor on the energy, only the elements of the mixing matrix. Okay. And just solving this problem, we get the number of suppression and also the value of the elements of the mixing matrix, which provide the achievement of this maximal suppression. We will get two answers, two outcomes. The first is the degree of suppression, and also under which condition, with which concrete numbers of the mixing matrix elements this condition is realized. Okay. Let's use the method of Lagrange multipliers. So we have to find, according to this method, one have to find the minimum of the following functional that is constructed accounting for this additional condition. So we have write the expression for the probability to the fourth plus this is the Lagrangian multiplier that should be determined, and here we write this condition in the following form. This is the sum I equal to 1 up to n, the squared mixing element minus 1, okay? And we have to find the minimum, so we have to determine first this multipliers, and then to find the final solution. So df over du ei equals to 0. So we have to solve, and including the exact expression. So we can write 4 the matrix mixing matrix squared to the third, yeah, by the fourth and to the third, plus 2 lambda. We have not 1, this expression, yeah, equal to 0. This is I equals to 1, 2, 3, etc. Yeah. Let's consider that n equal to 3 for simplicity. Yeah, but we can go to any n. Yeah, obviously. So we are not interested in. So just like this. This is 1. We are not interested in the solution without mixing. So we exclude this because there will be no suppression, yeah, obviously. If there is no mixing, there is no problem, nothing to discuss, yeah? So, and then we get that the square of the mixing matrix element equals to lambda minus 2, I equal 1, 2, 3. Okay? So, and just accounting for the condition that the sum of elements should be equal to 1, we immediately get that the modulus of the mixing matrix squared equal to 1 over n. Then the probability of survival of particular neutrino flux in its minimal value equals to, we just rewrite the expression, sum over I, the mixing matrix elements to the fourth in its minimal way equals to n multiplied by n squared equal to n. So we have obtained the following, that the maximal available suppression, degree of suppression, in the case of n flavor and n mass states of neutrinos is 1 divided by n. So it means that if n equals to 3, then the minimal achievable or the maximal achievable suppression is 1 over 3. And if you remember, Davis, who just measured the neutrino flux for the first time, he exactly reported that he has measured 1/3 of the expected number of neutrinos. So it means that his experiment was in a kind of ideal experiment, of course plus minus uncertainties of the experiment, but he just measured exactly the maximal possible suppression because there are 3 flavor neutrino states. Yeah. Okay. And now, just if we recall what I have already discussed with you about additional sterile neutrinos, yeah? If the fourth neutrino is present, it should be sterile neutrinos, but it will give a new option for suppression. If there is a fourth sterile neutrinos, it means that you can expect that in ideal experiment, it may happen that the suppression will be not 1/3, but 1/4. And this is a sign for experimental results, yeah? And if people see that the suppression is bigger than, exceed this 1/3, it means that there are some indication in favor of additional neutrinos. And these additional neutrinos, by definition, should be sterile, because from lab experiments, from the width of the boson, we know that active neutrinos could be only 3. No more. There is no room for the fourth active neutrino. So it's excluded. Well, and this is a kind of indication what kind of experiments should be organized in order to check whether the sterile neutrino exists or not, in principle. Yeah? Okay. Let's close this our discussion, and I would like to go further and discuss very, very important issue which is related to this oscillation phenomena. So for sure you see that the formulas that we and the theory, let's say, that we develop for the description of neutrino mixing in oscillations formally is very similar to expressions and mathematical formulas that we come across in optics when we consider the waves, the interference of different waves, etc. This is also the waves, but they have of completely different nature. Yeah, this is because we have wave functions, yeah, etc. Well, and these oscillation phenomena also suffering or exhibit an inherent constraints to appear due to the demands of coherence. So it is obvious that we just discussed an ideal picture, but in reality, if we just consider neutrino as a waves, we come to some constraints, in principle constraints, to observe the phenomena of neutrino mixing and oscillations, and these constraints come from the lack of coherence between two waves describing two oscillating neutrinos. And I would like to discuss with you now the limits that are set to appearance of this oscillation phenomena due to coherence and due to constraints that can be described as a demand of coherence between two interacting neutrino waves. So let's discuss, let's consider a kind of an experiment. Let's consider two neutrino species, two neutrino flavor neutrinos that are produced in a real experiment. These neutrinos are produced in interaction of particles. Let's suppose that these neutrinos appear in the decay of pi meson. So an experiment. A real experiment, so there is a pi meson decaying to muon with muon neutrino, yeah? And we are interested how this muon neutrino oscillate to electron neutrino. And we would like to derive the coherence constraint for the appearance of neutrino oscillation phenomena. So this is like a visual, this is a pion, a decay to muon, and this is the muon neutrino, yeah? So this is not a Feynman diagram, but it's like a visual image of what is happening, yeah? And this neutrino travel to a detector, and here we have muon or electron neutrino, yeah? And when there is an electron neutrino in the detector, we shall see electrons. Yeah, this is indication that some portion of muon neutrinos along this distance oscillate, transferred to another flavor, to muon flavor. Yeah, and if we found in the detector, find in the detector electrons, it means that some of muon neutrinos behave or just are visualized in the detector, measured as an electron neutrino due to neutrino mixing and oscillations. Yeah?
Maybe in instruction, no neutrino is anti-neutrino.
Yeah, of course. I can put like this, and this is the plus, okay? Of course. Thank you. So, let's suppose that we are smart and well equipped technically enough that we can exactly measure the momentum and energies of two particles, pions and muons, exactly, with very, very high precision, accuracy. Yeah? So let's suppose that the energies and momenta of pions and muons are measured. With very high precision. With very high precision, yeah? Okay, let's suppose that the combination for each particle, I mean muons and pions, energy and momentum are measured, very accurately are measured. In experiment. Well, it is quite reasonable. Why not? We can measure with the needed desired accuracy. Yeah. Then we can calculate everything about neutrino from the energy momentum conservation. Yeah. Obviously, if we measure two guys, we can immediately calculate what is the energy and what is the momentum of the emitted flavor neutrino. Okay? Okay. Then we suppose that the emitted muon neutrino are being the superposition of two mass states with the mass 1 or M2, and if we know everything about two guys, we can say for sure in which particular mass state the flavor neutrino, muon flavor neutrino appears, if we know everything, yeah? Okay, let's take this into account, and now come to the solution or examination of the problem of the coherence of two neutrino waves, and also derive the constraint for observability of neutrino oscillation pattern in any experiment. Just to solve this problem, we have to consider the difference of phases of two neutrinos of mass 1 and 2, because they propagate, yeah? Not flavor, yeah? The phase difference of neutrino 1 and 2. After this neutrinos travel a distance x from the point when they were produced to the detector. This is x, yeah? Okay. This phase difference depends on the distance and time of travel, and it can be expressed as the energy of neutrino 1 minus the energy of second neutrino over t minus the momentum of neutrino 1 minus momentum of neutrino t of neutrino 2. This is the phase difference of two waves, yeah? Oh, but we shall consider the direction that is described by the x coordinate. So we shall use the following notation that momentum, we have used the relativistic expressions, and also the energy equals to momentum squared minus plus the mass. Yeah? So, and now we would like to calculate the phase difference and then determine the condition of coherence, determine what it means. But obviously, the condition of coherence will be that the phase difference is somehow small. It's smaller than some basic number, whether 1, whether 2 pi's. For me, it's 2 pi's. Yeah, the maximal value of 2 pi's is much smaller than 2 pi's. Normally, people use the condition that this phase difference is less than 1. Yeah, but for me, it's more natural to compare this with the maximal available non-trivial value. This 2 pi's is the angle, and the maximum value is 2 pi's. Okay, but 2 pi's is more or less 1. It doesn't matter. If you just put much smaller, it doesn't matter. If it's 2 pi's, 1 pi, or just half a pi, it doesn't matter. Yeah? Okay, so first we have to determine this from the energy momentum conservation. We have to determine, to calculate, to estimate this the phase difference. So we use for this the energy momentum conservation, and how to. So the energy momentum conservation we write the following, that P pi equals to P nu plus P mu, where nu can be whether nu1 or nu2. Okay? From here we can get immediately that P pi minus P nu squared equals to P mu squared. And then for each of the neutrinos, nu1, nu2, we have a unique identical relation that the mass of the pine squared plus the mass of this particular neutrino, whether 1 or 2, minus 2 per pi per nu equal to the mass of mu squared. For nu equal to 1 or 2. Yeah. Okay. Then just combining, just accounting this relation twice for nu1 and for nu2, and we can get the consequence that the mass of neutrino 1 squared minus the mass of neutrino 2 squared minus 2, the momentum of pine, the momentum of neutrino 1 plus the same with another neutrino, nu2, equal to 0. So we get this expression. Yeah? So I just write this equation twice for nu1 and nu2, and then exclude one from another one. Then I will get 0, and here we get this very simple relation. Yeah? Okay. Now let's examine what this guy. So this per mu, p pi per nu equals to the energy of pine, the energy of particular neutrino, minus the product of three-dimensional vectors. And we consider pine non-relativistic, or even at rest. So it means that it is approximately the energy of pine, the energy of neutrino, where neutrino equals to neutrino 1 or neutrino 2. Non-relativistic, non-moving pine. We can just, without any concern, just consider this condition. And then we get very important relation that the difference of neutrino energies, neutrino 1, neutrino 2, equals to approximately neutrino mass squared 1 minus neutrino 2 squared divided by 2 energies of pine. This is very important relation for our consideration. Yeah. Okay, what we shall do further? Now we have to consider the second contribution to the phase difference that comes from the special term, yeah? The momentum multiplied by radius vector, and we consider that this is the momentum from neutrino 1 and 2 multiplied by x. So we consider that neutrinos propagate along x direction. And now we have some exercises. We account that the modulus of momentum of neutrino 1 or 2 equals to squared equals to the square of energy each of neutrinos minus the mass of each of neutrino squared. Yeah. Then we can write that the difference of momentum squared of neutrino 1 minus the neutrino 2 momentum squared equals to, just from these expressions, equals to the squared of neutrino 1 energy minus the second energy squared minus m neutrino 1 plus m neutrino 2. equals 2. And now we account for this expression and can go ahead and get, I just have to switch to the next screen, okay? And just if we to account this, we get, as a continuation of our evaluations, the following, that it can be expressed as neutrino energy 1, neutrino 2 energy, m1 squared minus m2 squared. I just use the short notations, yeah, I just skip neutrino indication. Neutrino 1 energy, it means neutrino energy 1, you understand, yeah? That's not to write these neutrinos every time. This is 2 energies of pions, of the pion in the denominator, minus, not forget about this, the mass of the first neutrino squared, the mass of the second neutrino squared, and then, just to some rearranged terms, we can get that m1 squared minus m2 squared divided by 2 energy of the pion multiplied by the energy of the first neutrino plus the energy of the second neutrino minus 2 energy of the pion. So that is more or less the end of the game. And finally, so we get that what we have interested in, the difference of the momentum of neutrino 1, 2 equals 2 can be expressed as the first neutrino mass squared minus the second neutrino squared divided by energy of the pion, double him, multiply by the energy 1 plus the energy 2 minus the energy of pion, multiply by 2 divided by sum of the neutrino momentum, yeah? Where I just recall that we just 1 or 2 is the modulus of neutrino 1, 2 momentum, yeah? Finally, we get that the phase difference, that is by definition is the energy of the first neutrino minus the energy of the second neutrino over T minus the momentum of the first neutrino minus of the second neutrino x equals 2. And we can just sum up all what we have derived. This is neutrino mass 1 squared mass 2 squared divided by 2 energy of the pion over T plus. Now I add and extract the same term and then rearrange all the terms. I just put something plus, the same minus, and then I arrange terms in order to make it more obvious the meaning of each of the term in the phase difference. I just put by hands the following m1 squared minus m2 squared divided by the sum of energies E1, E2 over T minus the same m1 squared minus m2 squared divided by energy 1 plus energy 2 over T. I just change nothing. Plus, minus the same, yeah? Minus the difference of momentum x equals, yeah? I just start with the term m1 squared minus m2 squared divided by the energy of the first neutrino plus the energy of the second neutrino, T. I just use one of the terms here. And then I have to include the rest. Yeah? And they can be written in the following form: m1 squared minus m2 squared divided by 2 energy of the point multiplied by the sum of energy neutrino 1, neutrino 2. And here I just should write E1 plus E2 minus double energy of the pine over T minus P1 minus P2 over X equals. So this is like a very, very, very trivial rearrangement of terms, yeah? Okay? And now the final step that enable us to write or express the phase difference in a very transparent for interpretation way, yeah? Finally, we get that the phase difference of two waves corresponding to neutrino of mass 1 and 2 equals to mass 1 squared minus mass 2 squared, the sum of the energies in the denominator over T plus momentum 1, momentum 2 multiplied by P1 plus P2 divided by sum of the energies 1 plus 2 over T minus X. This is the final expression for the difference of phases of two waves that describe neutrino of mass 1 and 2 when they propagate during time t and travel a distance x from the point when these two neutrinos were produced in some process we consider particular process of decay of pine. So this is what we have derived, and and now let's consider the interpretation of these terms and make the following observations. So it means the observation not from the point of the experiment, but theoretical observations, yeah? The meaning. So first of all, we can conclude that the second term is negligible for relativistic neutrinos. The first observation, the second term can be excluded for relativistic neutrinos. Neutrinos 1 and 2. Why? Because the distance x can be expressed as the velocity multiplied by t. And this velocity is exactly equals to the momentum 1 plus momentum 2 divided by the sum of energies. So this is exactly what we have here, yeah? I just explained probably in a more vivid way. So we can introduce gamma that is related to, according to the well-known expression, to the velocity beta squared, yeah? The gamma factor, yeah? This is a relativistic relation between the be at the velocity of an object. This is a gamma factor, yeah? So we also know that gamma is the energy divided by m, yeah? So then for beta squared we get just from here, we just make this very simple calculation, p squared minus m squared divided by p naught squared equals to momentum squared divided by p squared, yeah? Okay. So we can exclude. So this is the first observation, and then as a result we get that the expression for the phase difference is very much simplified. It is proportional, something equal to the mass square difference of neutrinos divided by two energies of neutrinos. This is the final expression of the phase difference when neutrinos travel distance from the source to the detector. Here we just use the obvious notation that is mass squared minus m squared, yeah? And E is the energy of neutrinos, okay? Okay. We also, this is what we get, yeah, as a solution, yeah? Then we can calculate the delta F, the delta F. So this is the variation, yeah, the difference. It depends just from this expression we can calculate. This is delta of mass square difference divided by two energy and T. And just using this is the constant. What can be changed? This is the energy. We can write that this is mass square difference divided by 2 delta 1 over energy. And we have to estimate what does it mean. So in order to estimate, we can say that the delta energy, the discrepancy between two energies, delta energy, is proportional to this description to delta of momentum. Yeah? Is proportional to the uncertainty in momentum. Yeah? Okay. And also, this uncertainty is determined by particular condition of the experiment. And using the Heisenberg uncertainty principle, we know that the uncertainty in the coordinate is related to uncertainty in momentum. So, and just from this, we can say that the uncertainty in momentum is inverse proportional to uncertainty of x. And this particular guy, we relate with the uncertainty in the point where neutrinos were produced. It depends on the conditions in the source, or if there is a neutrino from the sun, it means that this is uncertainty in the point where neutrinos were produced in the source. We have not a point-like source, but it is have some special dimension, so it means that we do not know exactly from which particular point neutrinos start to travel. Yeah? Okay, just using this, we can go further and write that the uncertainty in the phase equals to here we also have to make this estimation. We need to calculate delta of 1 over p, that is proportional to p squared, obviously, yeah, to delta uncertainty in momentum. And this guy, as we agree, is proportional to 1 over x, yeah? We have, okay, yeah? So, we use this and continue and write the following, that is a mass square difference divided by 2, 1 over momentum squared in denominator, delta momentum x equals to, finally I just write it like mass square difference divided by 2 momentum squared delta momentum x. This is a final expression for the difference uncertainty in the phase, in the point of arrival after the neutrino travel time or distance x. Yeah? And now let's introduce the criteria of coherence in order to have in principle possibility to observe the oscillation of two neutrinos. We introduce the coherence length. The coherence length. So we say that x equal to the coherence length when the difference of phases is small, and I put this criterion less than 2 pi's, or normally people say less than 1. But for me it's more natural to compare or much less, let's say. In fact, much less, yeah, as we always say, there's a limit, much less, but we shall use the criteria in the critical point, but it's equal, yeah, equal, or then to say this is less or much less, yeah? Okay. And now we can, after we just agree that the coherence length can be determined from this condition, that this delta phi less than 2 pi's, we can calculate the maximal number of maximas or minimas in the oscillation pattern. Yeah? So the maximal number of maximas or minimas in the oscillation pattern obviously is determined by the coherent length divided by the oscillation length, because the oscillation length is just the difference, spatial difference between 2 minimas or 2 maximas, and this is the number of oscillation maximals if we introduce this coherent length. Yeah, and now let's put everything here and derive the simplified expression here. We just put here 2 pi's, 2 momenta of neutrinos multiplied by 2 pi's divided by mass square difference squared delta of momenta. we should recall what is the oscillation length. We have introduced this and have written several types. 4 pi's in denominator momenta equals to momenta divided by delta momenta, that is proportional to the momenta multiplied by delta x. So I just recall that L1 and 2 oscillation length is 4 pi's, momenta or energy divided by mass square difference. We have used this. Okay? And of course, we just also should account for this prescription that energy is more or less equal to momenta. Yeah? And usually in experiment where oscillations are observed, in experiment, this is much more than 1, and we can see the oscillation pattern, and the coherence condition is fulfilled. Yeah? Just to close this discussion, I would like to add one more very important point here, and to prove and to show that it is not possible to even to think about the experiment with observing oscillations and simultaneously to see 2 peaks in the distribution of momentos corresponding to appearance of neutrino of the mass 1 and 2. You understand? If neutrinos, flavor neutrinos produced whether in the state of mass 1 or 2, there will be 2 peaks corresponding to each of particular neutrino of mass 1 and 2 in general. Yeah? But there is no, in principle, there is no possible to see in experiments these 2 peaks that correspond to the case that muon neutrino appears as neutrino of mass 1 or 2, and to see the oscillation pattern. This incompatibility simultaneously to see oscillations plus visualization in which particular neutrino mass species appears. Let's, according to this analysis, we can show that it's not possible. And this is an additional point that can be formulated as follows. The incompatibility of the experiment of невозможность, да, of experiment which detects on neutrino oscillations. So experiments that visualize or show us that there is an oscillation pattern, and determination, experiment on determination or visualization of double peak. In the measured particle energies, yeah? So each of the peaks correspond to each of the type of neutrino have been appeared, yeah? So Again, very precise experiment allows us to determine the energy plus or and momentum of pion and muon, yeah? And from, as we just discussed, from this we can say whether neutrino of mass 1 or 2 appears, yeah? Possible to see or to say neutrino 1 or neutrino 2, so corresponding to mass 1 or 2. So, and it means if we just measure the energy momentum of muons, if we determine in which particular mass state muon neutrino appears, we shall see two pikes in the spectrum of muons corresponding to whether neutrino is 1 or whether neutrino is of mass 2. 2 in muon spectra. It is clear, yeah? If you just very, very accurately measure the momentums, let's suppose that pion is at rest, and we measure the energy momentum for muons. And if we measure very carefully, we shall see in which particular mass states muon neutrino appears. The statement is, in this case, if we measure this, there is no room for neutrino oscillations to be observed, because in this case, the coherence criteria cannot be fulfilled. This is what I am saying, yeah? It is not possible simultaneously to see pikes and to see at least one maximum or minimum in the oscillation pattern. So it means that these two experimental conditions that in one experiment it is not possible to achieve. Whether this very sensitive to the spectrum or to oscillation pattern. So you can have only two different experiments. Once you measure in which mass state, there is no oscillation pattern. If there are oscillations, you will never say in which particular mass states neutrino have been observed. And this is inherent feature of quantum mechanics, by the way. This is quantum mechanics, yeah? Because we attribute to each particle, neutrinos, etc., the waves, yeah? This is quantum mechanical prescription. So let's show it by the very simple mathematical calculations. So, first, several steps, yeah, to make it more clear. The first step is to describe in which mass state a neutrino is emitted. So an exact determination in other words, I would like to exact determination of the momentum of pion less accurate location. So this is probably the appeal to the Heisenberg uncertainty condition. Yeah? If you manage to exactly determine the equations, this condition of motion and for initial particles and pions, so from this is obvious. The exact determination of momentum less accurate, you know, the location, vice versa. Yeah. And if you do not know exactly the location, you will never fulfill the coherence condition, as we discussed just before. This is the meaning, but the underground physics, yeah? When you fix the position of pion, in order to determine in which mass state neutrino appears, you will just, according to uncertainty condition, you will rule out the possibility for the coherence condition in the oscillation to be fulfilled. Okay, now let's supply all these words with the concrete mathematical formulas. Yeah, very simple. So the kinematic determination of the emitted neutrino is based the kinematic determination of neutrino state of emitted neutrino state is based on the well-known relation between the energy and momentum, that is, the mass state of neutrino equals to the energy of neutrino minus momentum of neutrino squared. Yeah, okay. Then the arrow, in order to distinguish whether neutrino in mass state M1 or 2, we have to consider the arrow in determination of the mass states. Yeah? From this relation, we can arrive that the arrow, uncertainty, in the mass determination is the following: delta m squared. We consider these two guys as independent values according to this fact. We can write that it's square of double energy neutrino, the uncertainty in neutrino energy, plus double momentum of neutrino squared, uncertainty in neutrino momentum, everything the square root, yeah? Then we have added to this plus the following, that two neutrinos M1 and 2 can be distinguished. Only can be distinguished. Only if the following condition is valid. So, the difference of neutrino mass uncertainty squared is less than the mass square difference. Huh? If not, you will never distinguish. So there's uncertainty in determination in this experiment of the mass state should be less than the mass codifference of real neutrinos. This is the criterion when you can distinguish neutrino of mass 1 and 2, obviously. This is an uncertainty in the measurements or calculations related to uncertainties in momentos and energies. And this is the values you should distinguish. In other cases, there is no, your uncertainty will not allow you to see whether neutrino is in mass 1 and 2 state, okay? This is this condition. Then we can write the following, that we are interested only in this part. We exclude this. We can't do this, yeah? We just put this value less than it is in reality. We just throw away this positive and write the same condition, but for sure it should be like this. We just write the square root of 2 momentos less than so this is a condition to distinguish. So we have to add, but we know that the uncertainty in momentum is inverse proportional to uncertainty in the coordinate. Then we can write from these conditions that the uncertainty in the coordinate should be not less than 2 momentum of neutrinos divided by mass codifference. That is the oscillation length. So, what is the result? So we come to the condition that the uncertainty in the location, this is the guy that describes the location of each particular neutrino emitted, is bigger than the oscillation length corresponding to this phenomena. So it means that there is no possibility, in principle, to observe oscillation pattern. So, and the final result is like this. It's not possible to simultaneously, in one experiment, to observe in each, to calculate by very accurate measurements of pion and muon state of motion, and to from this to see in which of mass states neutrino appears, and to see the oscillation pattern. But you can say this is obvious. Once neutrino is produced in a particular mass state, there is no oscillations, because the mass state survives forever, because the mass state is the eigenvalue for the Hamiltonian of neutrino evolution in vacuum. So if the muon neutrino or electron or other flavor neutrino are produced in a particular mass state, there is no room for oscillations, because this mass state will move as a mass state forever, any distance, any time. But we just make it in a more not complicated, but more accessible for experimental application, I should say. So, this put a limit. All these considerations put inherent limit to plan experiments for observation of neutrino oscillations. So it depends on the conditions when neutrino were produced, and it depends also on how accurate you can estimate the initial, the starting position of each neutrino. Well, I think that we shall close this part, and next time we shall go to a very important chapter or story in neutrino oscillation physics. We shall discuss how the presence of external environment matter influence neutrino oscillations pattern. And it's very important, and very important from a theoretical point of view, and also from practical applications for interpretation of real data from, let's say, solar neutrino fluxes, because inside the sun, the initial neutrino flux travels through quite dense matter, and as we shall see, matter can reasonably change the oscillation pattern, influence and new effects appears. Well, thank you very much.